We started looking at calculus to solve a problem, that problem being how do we find the slope of a tangent to a curve when we only know one point. But that introduced this idea of the derivative, and we said the derivative measures a rate of change. So any problem which involves a rate of change, if we can come up with a function or a graph that describes its motion or how it's changing, then we should be able to solve the problem using calculus. So let's look at an example here. We've got a block of ice in the form of a cube. I guess you would call that an ice cube. It has one edge 10 centimetres long, but it's melting. It's melting at a rate of 1 millimetre per second. So the question is how is this volume changing? Now, volume is not going to change at a consistent rate because it'll depend on how big the ice cube is at that point in time. The point in time we want to know is when the edge is 5 centimetres long. So, all right, how do we do this? There's my ice cube. I've just labelled the length x at any particular point in time. We want to know is what is dv to t. How does volume change with respect to time? We want to come up with a derivative for that. They've told me that the length of the ice cube changes at 1 millimetre per second. So that would be dx to t, how that x measurement changes with respect to time. It's negative because it's decreasing, getting smaller. And I've got to keep the units consistent. So I've made it 1/10, a millimetre being 1/10 of a centimetre. What I really need then is a link between volume and x. Because if I can now find dv dx, we can use that chain rule idea to come up with a formula. Well, we know volume will be x cubed. So dv dx would be 3x squared. So what I could say is, well, I want to work out dv to t. I know a formula for dv dx. You've given me some information about dx to t. That, in fact, if I multiply them together, you can think of it like, well, the dx's are cancelling. I've got dv to t. So my formula becomes 3x squared times negative 1 on 10. So negative 3/10 of x squared is the formula to find the rate of change of volume with respect to time. Now, we want to find out what it is when the edge is 5 centimetres long. So we sub in x equals 5, and we got minus 7.5. So we know that when the edge is 5 centimetres long, the actual volume at that point in time is decreasing at 7.5 centimetres cubed per second. So let's look at this one. A vessel is in the form of an inverted cone. Vertical angle 90 degrees. Depth of the water in the vessel is x centimetres. Find the volume of the water. Well, it's always a good idea with these sorts of things to draw a picture, I think, so you can get your head around the problem. So if you can draw some sort of a picture. Inverted cone. There's my water sitting in there. We know it's a right angle at the bottom. They told us that. Vertical angle of 90 degrees. Vertical height is x. We want to find not the volume of the whole vessel, but just the volume of the water there. Volume of a cone, 1/3 pi r squared h. We're going to need the radius. So we're going to have to work out the radius here. So if I draw one across, but if we look at that, it must be a 45-degree isosceles triangle because it would cut that 90 in half. So actually the height and the radius would be the same in this particular problem. So I know that's going to be x as well. So volume, as you told me, 1/3 pi r squared h, sub the x's in. So for this problem, we can say the volume of the water is 1/3 pi x cubed. Okay. So we're pouring water in at a constant rate, so pouring it in, but the depth of the water is not going to change at a constant rate because of the shape of the vessel. So we want to know how's the depth changing when the depth gets to 4 centimetres. So the depth, which is x, is dx to t is what I want to find. What have I got? Well, dv to t, rate pouring in. Again, got to make sure the units are okay. 0.2, I'll write it as a fraction, 1/5. We can also find dv dx, because back in part A, we worked out a formula that links volume and x together. So if I differentiate v with respect to x, we get pi x squared. That should be enough to work out dx to t. So dx to v times dv to t. Well, if I turn dv dx upside down, I got dx to v. So it'll be 1 over the pi x squared times the fifth. There's our formula for dx to t. We want to know when x is 4 centimetres. So sub in x equals 4, and there's a lovely exact value of 1 on 80 pi. So we know it's increasing at 1 on 80 pi, and the units would be centimetres we used for length, minutes we've used for time there, so centimetres per minute. 7H there.